Alright, let's go. Number 12. The Antimatter Asymmetry Cover. The base collaboration at CERN spent nearly a decade building a penning trap, a device that suspends a single antiproton between magnetic and electric fields, holding it motionless in a vacuum colder than the space between galaxies. Their job was routine metrology. Measure the magnetic properties of one antiparticle. Compare it to the proton. File the number. If antimatter is the exact mirror of matter, its magnetic moment should be identical in magnitude and opposite in sign. Every version of the standard model requires this, a principle called CPT invariance, one of the most rigorously tested in all of physics. Break it, and you explain why the universe survived at all. Matter and antimatter should have annihilated completely in the first microsecond after the Big Bang. The measurement came back after years of runs. The antiproton and proton magnetic moments matched to 1.5 parts per billion. No asymmetry. None. The symmetry held at a precision better than any previous antimatter test by a factor of 350. Christian Smora and the base collaboration published the result in Nature in October 2017, the most precise measurement of any property of any antimatter particle ever performed. Stefan Ulmer led the group. The number disagreed with theoretical prediction by less than the width of a proton's shadow. It was, and remains, the strongest experimental confirmation that antimatter obeys the same magnetic laws as matter. Every proposal to explain the leftover matter has broken. Andrei Sakharov's 1967 conditions require CP violation in the early universe. CP violation exists, but the measured amount from B. Meson experiments at LHCb and Bell II falls short of what's needed by roughly 10 orders of magnitude. Leptogenesis requires heavy right-handed neutrinos no experiment has detected. Electroweak baryogenesis needs a first-order phase transition the measured Higgs mass rules out. Every mechanism proposed since Sakharov has failed to test produced too little asymmetry or demanded particles that refuse to appear. Every atom in your body is a survivor of an event no physicist can currently explain. For every billion matter-antimatter pairs produced in the first instant, roughly one matter particle remained. That left over is you, your desk, the light from the sun. The rest of the universe annihilated itself and vanished before the first second was finished. If matter and antimatter behave identically at every measurable precision, where did the asymmetry come from? And why has no one been willing to answer that out loud? The pattern holds, the anomalies get published, then buried in silence. Number 11. The Galaxy Without Dark Matter. In 2018, Peter Van Dokkum's team at Yale was conducting a survey with the Dragonfly telephoto array, a homemade instrument built from Canon telephoto lenses arranged into a wide-field imaging system designed to catch low-surface brightness galaxies. They found one. It was faint, diffuse, unremarkable in most respects. They pointed larger telescopes at it and began measuring how fast its globular clusters were moving. In every galaxy ever measured, the outer stars and clusters orbit faster than visible matter can account for. This is the observation that produced the dark matter hypothesis in the first place. Vera Rubin's 1970s rotation curves showed the discrepancy across the entire sky. If dark matter is a universal, indispensable component, it must be present in every galaxy of sufficient size. The clusters in NGC 1052 DF2 were moving slowly. Too slowly. Their velocities were exactly what the visible stars alone would predict. No dark matter signature at all. Van Dokkum published the finding in Nature in March 2018 under the title A Galaxy Lacking Dark Matter. The velocity dispersion of the 10 globular clusters was measured at 8.4 kilometers per second, consistent with zero dark matter within measurement error. A follow-up 2019 paper in the Astrophysical Journal Letters extended the result to a second galaxy, NGC 1052 DF4, from the same group. The response was hostile. A team led by Nicholas Martin argued the distance had been mismeasured. If the galaxy were closer, the velocities would imply dark matter after all. Van Dokkum's group redid the distance measurement using 5 independent methods, including tip of the red giant branch. The galaxy sits at roughly 22 megaparsecs. The dark matter is still missing. Others proposed tidal stripping by a larger neighbor. Simulations couldn't reproduce the observed structure. Modified gravity theories, meanwhile, cannot produce a galaxy without dark matter, because they don't allow for dark matter in the first place, so its absence is a headache, not a prediction. If dark matter is a substance, some galaxies have it and some don't, which raises the question of what selects them. If dark matter is a modification of gravity, this galaxy cannot exist. The universe you are living in either contains an invisible substance that behaves capriciously, or a law of gravity that fails in specific places. How do you build a galaxy without the ingredient that supposedly built every other galaxy in the observable universe? One anomaly can be a measurement error. When they compound, the story changes. Number 10. The structured vacuum. In the late 1980s, Bernhard Heisch, an astrophysicist at Lockheed, was working through problems in stellar coronal physics. He teamed up with Alfonso Rueda, an engineer, and Harold Puthoff at the Institute for Advanced Studies in Austin. They were not looking to overturn Newton. They were trying to explain why certain classical predictions kept failing at the boundary between electromagnetism and mechanics. Newton's second law, force equals mass times acceleration, treats inertia as an intrinsic property of matter. Push a mass, and it resists. The resistance comes from the object itself. This assumption is baked into every equation of motion from Newton to Einstein. Mass has inertia because mass has inertia. There is no deeper explanation offered by the standard framework. The three researchers derived, from first principles, that inertia could be a reaction force, not intrinsic. A resistance produced by an accelerating charge interacting with the zero-point field of the quantum vacuum. The equations closed. The prediction reproduced Newton's law as a limiting case. Heisch, Rueda, and Puthoff published inertia as a zero-point field Lorentz force in Physical Review A in February 1994. The paper passed peer review at one of the most respected physics journals in the world. NASA's Breakthrough Propulsion Physics program funded a follow-up study in the late 1990s. The study confirmed the mathematical framework was internally consistent. Funding was discontinued in 2002. The program was shut down. Critics argued the derivation required arbitrary assumptions about the vacuum spectrum. Heisch and Rueda responded with a 1998 paper showing the assumptions were the minimal ones consistent with Lorentz invariance. Others argued the theory made no new predictions. The team then proposed an experimental test involving asymmetric Casimir cavities. No laboratory has performed the test at the required sensitivity. The theory was not refuted. It was ignored. Puthoff continued working on it into the 2000s and 2010s, with occasional publications in peer-reviewed venues. The mainstream response was silence. No competing theory of inertia's origin was proposed to replace it. The question was simply removed from the list of things worth funding. The reason your body resists being pushed, the reason a car accident hurts, may not come from your body at all. It may come from the vacuum around you, pushing back through a mechanism no textbook explains and no laboratory has been funded to definitively test. If the resistance you feel when you push a wall comes from empty space, what happens to that resistance when the space around you is not empty? The next case involves something more basic than inertia, whether the universe is even expanding. Number 9. The non-expanding universe. Christoph Wetterich is a theoretical physicist at Heidelberg University, best known for foundational work on quintessence and dark energy. In 2013, he was working through the mathematics of scale invariance in cosmology, asking what happens if certain fundamental parameters are not fixed constants but slowly varying fields. The standard cosmological model treats the redshift of distant galaxies as evidence of universal expansion. Photons emitted long ago arrive stretched, their wavelengths lengthened by the growing distance between us and their source. This is the foundation of the Big Bang framework, of the accelerating universe, of dark energy, of the entire modern cosmological project. The redshift is real. The interpretation is that space is expanding. Wetterick showed the same redshift can be produced by a universe that is not expanding at all if the masses of atoms increase over time. Everything gets heavier, atomic spectra shift, distant light appears redshifted. The math works. The two models are observationally indistinguishable. Wetterick posted the paper, A Universe Without Expansion, to RxIve in June 2013. It has been discussed in the theoretical cosmology literature since. It carries roughly 40 citations to date. Papers proposing modifications to dark energy or inflation frequently accumulate thousands. The framework has not been mathematically refuted. It has been rhetorically dismissed on the grounds that it is less natural than expansion, though no formal metric of naturalness has been applied. Steven Weinberg reportedly acknowledged the framework was self-consistent, but expressed skepticism about its motivation. Others noted the paper predicted the same observations as the standard model, which was framed as a weakness rather than a feature, a curious argument given that reproducing all confirmed observations is normally called a strength. Sean Carroll wrote publicly that Wetterick's model was interesting but not the way physics is done. No paper has produced a distinguishing observation. No experiment has been proposed to test it. Wetterick himself has continued publishing extensions of the framework. The responses have been polite dismissal, not engagement. The theory remains as consistent and as ignored as it was in 2013. Every redshift you have ever seen, every image of a distant galaxy tinted red in a textbook, has an alternative explanation that no one has ruled out. The universe you were taught to picture may not be growing. The atoms in your body may be getting heavier instead. If the redshift can be explained without expansion, what part of the Big Bang narrative rests on evidence and what part rests on habit? If distances aren't growing, our star may not be doing what we assume either. Number 8. The electric sun model. Ralph Jurgens was an engineer, not an astrophysicist, working in the early 1970s. He had followed the debates around plasma physics initiated by Hannes Alfvén and Christian Birkeland, and he noticed a specific mismatch in the standard model of the sun. The corona is hotter than the surface by a factor of hundreds. This is not a small anomaly. It is a violation of ordinary thermodynamics as applied to a purely thermonuclear star. The standard solar model treats the sun as a self-gravitating ball of plasma powered by hydrogen fusion in the core. Heat propagates outward through radiation and convection. By the time energy reaches the surface, the photosphere, the temperature is around 5,700 Kelvin. Above the surface, in a diffuse region called the corona, the temperature should keep falling. It doesn't. It jumps. The corona reaches temperatures of 1 to 3 million Kelvin, above a surface that is hundreds of times cooler. This has been directly measured repeatedly for over 70 years. The temperature discrepancy has been confirmed by every major solar observatory, SOHO, TRACE, and most recently the Parker Solar Probe, whose 2019 and 2021 findings appeared in Nature Astronomy. The mainstream explanations are Alfvén wave heating and nanoflare reconnection, first developed by Eugene Parker in a 1988 Astrophysical Journal paper. Neither has been definitively confirmed. Jurgens proposed in 1972 that the sun is partly powered by electrical discharge from an interstellar current, a model in which the corona is the anode plasma of a cosmic circuit. Jurgens' specific model was published in a non-mainstream venue and never engaged with by the astrophysics community. No formal refutation was published, but no serious testing was conducted either. Parker's nanoflare theory has drawn partial evidence from solar dynamics observatory data, though the total energy budget from nanoflares appears insufficient to fully heat the corona. Alfvén wave heating requires wave modes that have been observed, but at intensities not yet reconciled with the required temperatures. Every serious proposal, mainstream or otherwise, has produced partial results and stopped short of closure. The sun's atmosphere remains hotter than its surface by an amount that no complete model predicts from first principles. The star you can see with your eyes, the source of every calorie you have ever eaten, is doing something above its surface that its accepted physics does not fully account for. This has been the case for 7 decades. It is discussed in specialist journals. It is not discussed in introductory textbooks. if the corona heating problem has resisted resolution for 70 years? What does that suggest about the confidence of everything else we teach about the sun? The sun is one anomaly. The speed of light itself is another. Number 7. The variable speed of light. In the late 1990s, Ju Mugwejo, a young theoretical physicist at Imperial College London, was working through the horizon problem, one of the foundational puzzles of cosmology. He was collaborating with Andreas Albrecht at UC Davis, a co-inventor of the inflationary model. Together, they began asking whether the standard solution to the horizon problem, cosmic inflation, was the only possibility, or the least strange of several. The observable universe is extraordinarily uniform, regions on opposite sides of the sky, which have never had time to exchange light or heat, share the same temperature to within 1 part in 100,000. This is the horizon problem. Something must have connected them causally in the past, or the assumption that the speed of light is constant must be revisited. Standard cosmology solves the puzzle by proposing inflation, a period of exponential expansion that stretched a tiny causally connected region into the entire visible universe. Mugwejo and Albrecht proposed a different solution. The speed of light was higher in the early universe. If light traveled faster before, distant regions could have exchanged information without inflation. The horizon problem dissolves. Their paper, A Time Varying Speed of Light as a Solution to Cosmological Puzzles, was published in Physical Review D in February 1999. The framework was mathematically consistent, produced testable predictions distinct from inflation, and made specific claims about how the cosmic microwave background power spectrum would differ. Mugwejo went on to publish a technical monograph, and in 2003, a popular book. Albrecht continued to work on inflation and on the variable constants framework in parallel. The response from the cosmology community was largely dismissive. André Linde, one of the architects of inflation, argued the variable speed of light framework was less predictive. Mugwejo countered that inflation itself requires an inflaton field with parameters chosen by hand. No definitive observation has ruled out either model. The microwave background data is consistent with both, within current precision. Inflation received billions of dollars in observational and theoretical investment across 3 decades. Variable speed of light received a handful of postdocs. The predictions that would distinguish the two remain unmeasured. A constant you memorized in school, the speed of light in vacuum, 299,792,458 meters per second, may not be a constant across cosmic time. If it changed, every calibration of distance, age, and energy in your universe changes with it. The clock you were handed may have been running at a different speed when time began. If the strongest test of a physical constant is the assumption that it doesn't vary, how would we ever discover if it does? The framework Alfvén built extends beyond photons. Number 6. Plasma cosmology. Hannes Alfvén was a Swedish physicist who won the Nobel Prize in 1970 for founding the field of magnetohydrodynamics, the study of electrically conducting fluids in magnetic fields. His work is used every day in fusion research, in modeling the solar corona, in understanding planetary magnetospheres. In the last 2 decades of his career, he turned to cosmology, arguing that the same electromagnetic forces that dominate 99% of visible matter should also dominate the largest structures in the universe. Modern cosmology treats gravity as the dominant force on cosmic scales. Galaxies cluster because they attract. Dark matter provides the extra gravitational pull needed to hold them together. Electromagnetic forces are treated as small corrections, significant near stars, negligible between galaxies. The universe is a gravitational structure with electromagnetic decoration. Alfvén argued the reverse. Plasma, ionized gas, fills space, conducts current, generates magnetic fields, and organizes itself into filaments. He predicted that large-scale cosmic structure would appear filamentary, not homogeneous. He predicted this in the 1960s. Redshift surveys in the 1980s and 1990s confirmed the filamentary structure now known as the cosmic web. Alfvén's prediction of filamentary structure appeared in his 1990 book Cosmic Plasma and in earlier papers through the 1970s. Confirmation came from the CFA Redshift Survey in 1985, the Las Campanas Redshift Survey in 1996, and eventually the Sloan Digital Sky Survey. The prediction was made 2 decades before the observation. LFN did not receive credit for it. The filamentary structure was attributed to dark matter simulations that reproduced the pattern by tuning gravity-only models. Plasma cosmology has never received the observational program its predictions arguably warrant. Alphean students, including Anthony Perrott at Los Alamos, continued the research through the 1990s. Perrott's simulations of galaxy formation from plasma currents were published in IEE Transactions on Plasma Science, not in mainstream astrophysical journals. The result was predictable. Mainstream cosmology never engaged with the model directly. Instead, dark matter and inflation absorbed the phenomena plasma cosmology aimed to explain. Alphen predicted this outcome himself. In his Nobel address and later writings, he described the mainstream response to his cosmological work as a case of establishment inability to accept new ideas from outside a narrow disciplinary boundary. The intergalactic medium, the plasma between galaxies, carries currents, generates magnetic fields, and connects structures across billions of light years. A framework in which those currents are causal, not decorative, was developed by a Nobel laureate and left largely untested at cosmological scales. If a Nobel laureate's cosmological framework can be ignored for 50 years without formal refutation, what protects the framework that replaced it? Some physicists went further still, beyond matter, beyond fields. Number 5. The digital physics hypothesis. Edward Fredkin was a computer scientist and physicist at MIT, founder of the Digital Physics Group, who spent decades arguing that the universe is fundamentally discrete, not continuous. In 1982, he and Norman Margulis published foundational work on reversible cellular automata, computational systems that operate under the same information preservation rules physics obeys. Stephen Wolfram took up the same thread from a different angle, working through the mathematical space of possible rules. Standard physics treats space and time as continuous, infinitely divisible, described by differential equations. Every field, every particle, every trajectory is a smooth function of real numbers. Quantum mechanics adds discreteness for certain observables, but the underlying space-time remains continuous in every mainstream formulation. This is the picture from Einstein to modern quantum field theory. Fredkin and Wolfram argued the underlying substrate is a cellular automaton. Discrete cells. Discrete updates. Discrete rules. Physics as we know it emerges from computation running at a level below spacetime. Wolfram published A New Kind of Science in 2002, a 1,197-page technical treatise arguing that simple computational rules can produce every observed feature of physical law. No mainstream journal would peer-review the work at its required length. It was self-published. Wolfram followed up in 2020 with the Wolfram Physics Project, which proposes specific hypergraph rules underlying quantum mechanics and general relativity. Papers from the project have appeared on RXIV. The framework has not been formally refuted. It has also not been formally engaged with by most working physicists. Critics argue the framework is not falsifiable at its current stage of development. Wolfram's response is that falsification will come once the specific rule set is identified, and searching the rule space is a matter of computation time. Others argue the model has produced no novel testable prediction. Wolfram's team has published proposed observational tests involving quantum gravity signatures and discrete spacetime effects. The tests sit at the edge of current experimental capability. Fredkin himself continued to publish into the 2010s. Neither approach has attracted large-scale institutional funding. Neither has been ruled out. The community response has largely been to change the subject. The screen you are reading this on runs on computation. Every simulation of a physical system your civilization has ever produced runs on computation. Whether the substrate of reality itself is also computational, whether your body is a pattern of updating cells rather than a continuous flow of matter, is a question serious physicists have asked and been quietly told not to publish loudly about. If the universe is a computation, what is running it, and does the answer belong to physics or to something else entirely? If the universe computes forward, some equations quietly compute backward. Number 4. The retrocausal interpretation. Yakir Aharonov, working with Peter Bergman and Joel Lebowitz at Yeshiva University in the early 1960s, was trying to make sense of the arrow of time in quantum mechanics. The equations were symmetric. They didn't distinguish forward in time from backward in time evolution. Measurement outcomes appeared to. Aharonov asked whether the asymmetry was fundamental or an artifact of how the theory was being applied. Standard quantum mechanics treats the wave function as evolving forward in time, updated by measurement. The measurement is a boundary condition imposed by the observer at a specific moment. Causes precede effects. Information flows forward. This is what every textbook teaches, from Griffiths to Sakurai. Aharonov, Bergman, and Lebowitz derived a formalism in which quantum mechanics is time-symmetric. Future measurements impose boundary conditions on present states, exactly as past measurements do. The equations work identically in both temporal directions. The paper time symmetry in the quantum process of measurement was published in Physical Review in June 1964. It laid the foundation for what became the two-state vector formalism. Aharonov, Sandu Popescu, and Jeff Tollickson published a major extension in Physical Review A around 2010, providing experimental protocols. Weak measurements, a specific technique the framework predicts, have been performed by Ephraim Steinberg at the University of Toronto and others, with results consistent with retrocausal predictions. The interpretation is described in graduate quantum mechanics textbooks and immediately dismissed. Critics argue it introduces philosophical weirdness, signals from the future, causes from effects. Aharonov's response is that the philosophical weirdness of standard quantum mechanics is not smaller, only more familiar. Others argue the two-state formalism is mathematically equivalent to standard quantum mechanics, and therefore adds nothing. Aharonov's team responded with predictions that differ from standard interpretations for specific experimental setups, predictions that have been partially confirmed. The interpretation continues to appear in specialist literature. It does not appear as a viable option in most introductory courses. The reason offered is that it is too strange. No stronger reason has been published. The choice you make tomorrow may, in a formally consistent quantum framework, be exerting a boundary condition on the state of your body today. Not metaphorically. Mathematically, the formalism has been in the literature for 60 years. If the equations of quantum mechanics run identically forward and backward in time, why do we teach that they only run one way? Time is one problem. Consciousness is the next. Number 3. Panpsychism as physics. David Chalmers, then at Washington University in St. Louis, was working through what he called the hard problem of consciousness. The question of why physical processing produces subjective experience at all. Every other property of the mind, in principle, could be explained by neural function. Redness itself, the felt quality of red, resisted every framework Chalmers examined. In 1995, he published a paper arguing that consciousness could not be reduced to physical function and might instead be a fundamental property of reality. The standard physicalist framework assumes that consciousness emerges from complex information processing. Enough neurons wired the right way, and awareness happens. This is the assumption underlying most of cognitive science, neuroscience, and artificial intelligence research. It is treated as obvious. It is not, in fact, obvious. Chalmers argued that no arrangement of physical components, however complex, produces subjective experience if experience is not already present at the base level. The emergence claim, examined carefully, does not survive scrutiny. Something has to be added to the ontology. Chalmers' paper facing up to the problem of consciousness appeared in the Journal of Consciousness Studies in 1995. Giulio Tononi at the University of Wisconsin published Integrated Information Theory in 2004 in Biological Bulletin, formalizing the idea mathematically. Tononi's theory produces a specific quantity, phi, that measures the degree of integrated information in a physical system. Christoph Koch, formerly at Caltech, now at the Allen Institute, has publicly defended it as a candidate physical theory of consciousness for 2 decades. The mainstream neuroscience community treats the framework as philosophical rather than scientific. Critics argue phi is uncomputable in practice for any system large enough to matter. Tononi's team has responded with computable approximations. Others argue the theory has no experimental predictions. It does predict specific patterns of neural activity should correlate with reported consciousness, predictions that have been tested at Wisconsin and elsewhere with mixed but non-null results. Physics departments, meanwhile, refuse to schedule these presentations as physics. They are filed under philosophy of mind. No physics faculty position at any major research university has been created explicitly to test consciousness as a physical variable. Every experience you have had, the color of the sky at dusk, the taste of the last thing you ate, is in one serious framework. A property as fundamental as electric charge. Every institution capable of testing this refuses to. The question of whether your inner life is physics has been declared not physics by the people who decide what physics is. If consciousness cannot be reduced to physical function and cannot be studied as a physical property, what field is it supposed to belong to? Consciousness is difficult. Direction is measurable. Number 2, the universe's preferred direction. Lior Shamir is a computer scientist at Kansas State University who developed image analysis software for large astronomical surveys. His approach was straightforward. Take a catalog of galaxies with resolved morphology. Determine for each spiral galaxy whether its arms win clockwise or counterclockwise as seen from Earth. Count, if the universe is isotropic, the count should match. The cosmological principle, the foundational assumption of modern cosmology, states that the universe is homogeneous and isotropic on large scales. No preferred position, no preferred direction. Every mainstream cosmological model, from the Big Bang to inflation to dark energy, is built on this principle. It is not usually presented as an empirical result. It is presented as a starting condition. Shamir's analysis showed the counts do not match. In a sample of more than 200,000 galaxies, there was a statistically significant excess of galaxies rotating in one direction relative to Earth. The asymmetry varied with sky position, tracing what looks like a cosmic axis. Shamir published a series of papers, notably in monthly notices of the Royal Astronomical Society in 2020 and in publications of the Astronomical Society of the Pacific and other venues through 2022 and beyond. The statistical significance of the asymmetry was reported at greater than 3 sigma in the largest samples. The dipole pattern's axis approximately aligned with other anomalies previously identified in the cosmic microwave background, the so-called axis of evil first reported by Kate Land and Ju Mugwejo in 2005 in Physical Review letters. Critics argued Shamir's automated classification was subject to systematic bias, that the software preferentially detected one chirality over another for reasons unrelated to the galaxies themselves. Shamir responded by manually reclassifying subsamples and by cross-checking against different survey instruments. The signal persisted. Others argued the effect could arise from local structure, the Milky Way's orientation biasing observation. Shamir addressed this by analyzing galaxies at varying distances. The signal appeared at cosmological ranges. No definitive systematic has been identified. No follow-up survey has been funded to test the effect at higher precision. The cosmological principle has not been formally revised. The universe you have been taught is symmetric may have a preferred axis, a direction running through the sky that violates a foundational assumption underlying every calculation of cosmic age, distance, and structure. The observational signal exists in published data. The theoretical response has been silence. If the universe has a preferred direction, what determines it? And what does its existence mean for a cosmology built on the assumption that no direction is preferred? The final entry connects every problem on the list. Number 1. Consciousness as a fundamental force. Roger Penrose, Nobel laureate in physics, and Stuart Hameroff, an anesthesiologist at the University of Arizona, were collaborating on a specific question that neither field alone could answer. Penrose came from mathematical physics. He had argued in The Emperor's New Mind in 1989 that human cognition included non-computable operations, meaning it could not be simulated by any algorithm. Hameroff came from clinical anesthesia. He studied what actually turns consciousness off in the operating room. The mainstream view of consciousness treats it as a byproduct of neural computation, a functional state produced by patterns of firing across networks of neurons. Anesthesia is described as disruption of these networks. The classical physics of the brain, sufficiently complex, produces awareness as an emergent property. This is the framework taught in every major medical school. Penrose and Hameroff proposed that consciousness is not classical. It arises from quantum coherence inside microtubules, cytoskeletal structures inside neurons, and specifically from a process Penrose called objective reduction, in which quantum superpositions collapse under gravitational influence at a specific mass-energy threshold. The theory, formally called orchestrated objective reduction, or ORCH, was developed through a series of papers beginning in 1996 in the Journal of Consciousness Studies. Anirban Bandyopadhyay at Japan's National Institute for Materials Science reported evidence around 2013 of resonances in microtubule structures, discussed in Physics of Life reviews with peer commentary. Jack Tazinski at the University of Alberta and collaborators have reported further experimental evidence consistent with non-trivial quantum effects in microtubule structures. In 2024, work at Wellesley College reported that microtubule stabilization altered the time to unconsciousness under anesthesia in rats, a prediction ORCH makes. Max Tegmark at MIT published a widely cited 2000 paper in Physical Review E, arguing that decoherence times in warm, wet biological systems would be too short to sustain quantum coherence. Penrose and Hameroff responded with a paper identifying errors in Tegmark's calculation, specifically the assumption that microtubule interiors are electrically identical to bulk cellular fluid. The debate has continued. Neither side has produced a decisive experiment. The Wellesley rat study is the strongest single piece of experimental support and is not yet fully reproduced. No laboratory has openly funded a full-scale test. The awareness you are experiencing right now, the sense of being present in this moment, may be a quantum phenomenon operating inside the cytoskeleton of neurons in a way no mainstream physics or neuroscience department will publicly fund to a definitive test. The most consequential question you can ask about your own existence has been placed off the funding map. If the physical basis of consciousness is a testable question, and no institution will test it, is the question being avoided because the answer might be inconvenient? Every entry on this list is a published, peer-reviewed, mathematically consistent challenge to what modern physics teaches. None has been decisively refuted. None has been decisively confirmed. The universe is not confused. We are. And the pattern is not that the frontier is hard. The pattern is that certain questions have been quietly removed from the frontier, not because the answers are known, but because the answers might not fit the framework that already claimed the funding. If you want to see more videos like this, click the video on screen now.